download our Revise It Right revision app for hundreds of videos, quizzes, exam questions, tutor support and so much more. This video is about electric fields. Now all charged objects have an electric field, and an electric field is created around any electrically charged object. Now you can show an electric field around an object using field lines, and I'm going to do that for you now. So here I'm going to draw a positively charged object. Now it's important to remember that in a positively charged object, the electric field lines point away from the positive charge. So the electric field lines point this way in a positively charged object. Now in a negatively charged object, the electric field lines point towards the object. So here is a negatively charged object. And here now we can see that the electric field lines are pointing towards this object. So remember that all charged objects have an electric field around them. To display this, we can use electric field lines. They point away from a positively charged object and they point towards a negatively charged object. Now the closer to the object you get, the stronger the field is. So for example, if we were to place an object here, that would feel a much stronger electric field force than if we were to place an object here because it's closer. So the closer to the object you get, the stronger the field is. And the further you are away from it, the weaker the field is. Now, a non-contact force is experienced by a charged object placed inside the electric field of another object. So when a charged object is placed in the electric field of another charged object, it feels a force. So here I'm going to draw a positively charged object. And here we know that the electric field items are pointing away from. And what we're going to do is we're going to place another object here in the electric field of that object. And this one is also going to be a positive charged object, so the electric field lines are going to be going away from the object. Now when you place an object into the electric field of another object, a non-contact force is experienced. And this force causes either an attraction or a repulsion. Now it will cause a repulsion if the two charges are the same. So for example, here we've got a positive object and a positive object. So the force experienced here will be repulsion and they will want to move away from each other. And again, if we were to draw two negatively charged objects, and remember we draw these by pointing the arrow, the electric field line goes towards the object. If you place this within the electric field of each object, again because they're both the same charge, they're both negative, the force experienced, the non-contact force experienced will be repulsion as well. So again, they will want to move away from each other. But if you put a positive charge into the electric field of a negatively charged object, what will happen is the force experienced will be that of attraction. Now it is the electric fields of the object, so these electric field here, they show the electric field lines, it is the electric fields of each object interacting with each other that causes this attraction or repulsion. Now it's important to remember and understand that the size of the force between the objects is linked to the strength of the electric field at that point. So for example, let me draw another electric field here. And we know that this is going to be positive because the electric field lines are pointing away from the object. The closer these lines are together, the stronger the electric field. So for example, if I were to do this object here, and these lines show the electric field, and these are all pointing away again, and therefore we know it's a positive object. And then I were to draw this object here, and again it's positive. the electric field from this object is greater and stronger than this object because these lines are closer together. So the closer the lines are together, the stronger the electric field. Now you can see from hopefully this figure that the further you go away from the object, the further apart the lines are. So for example, if we compare this point here, where the lines are quite close, to this point here, where the lines are further away. So what this tells you is that the further away you are from the object, the weaker the electric field, because the lines are further away from each other. And it's the same in all of these points. So here, if we look at this chart here, the lines are closer together here than they are here. And therefore, the field is stronger here and weaker here because the electric field lines are closer together here. Okay, so the closer the electric field lines are together, the stronger the electric field. And therefore, as you move away from an object, the electric field gets weaker because the electric field lines get further away from each other. And also remember, of course, that two positive objects will repulse. They will experience a non-contact force of repulsion when they enter each other's electric fields. Two negative objects, again, will feel that force of repulsion when they enter each other's electric fields. And a positive and a negative will experience a non-contact force of attraction when they enter each other's electric fields. And the further away from an object you go, the weaker the electric field, because the electric field lines are further away from each other. Remember to download our Revise It Right revision app, watch over 700 videos, answer 4,000 plus quiz questions, over 1,000 flashcards, 1,000 exam questions, worksheets, forums, and get help from qualified teachers and so much more. The link is in the description. Now, sparking, as you've seen in the previous video on static electricity, and if you haven't watched it, then please go back and watch it. As we said, is caused when there is a high enough potential difference between a charged object and the earth. So for example, this car here has a charge, and the earth, remember, has a charge of 0 volts. So there is a high enough potential difference between this car here and this earth for there to be a spark. Now, what this high potential difference does is causes a strong electric field between the charged object and the earthed object. Okay, so this here, this charged object, this car, is going to have a very strong electric field, and the person here are going to have a strong electric field between them. Now, what this strong electric field does is it causes the electrons in the particles in the air. So we know that the air is made up of different particles. We know it's made up of nitrogen and oxygen, and it causes the electrons in these particles to be knocked off. So electrons to be knocked off of these particles. Now that gives these particles in the air a charge, because air is normally an insulator, but when it is ionized, i.e. when it loses the electrons, it has a charge and it's suddenly more conductive, and it can conduct electricity. So what that means is the charge can flow through it, and this is what a spark is. So the charge can jump from the car to the person that's touching the car, and then flow to the ground like we looked at in the last video. And it can go through the air because the air particles have had electrons knocked off of it and has therefore become more conductive. So this can happen because the electric field between the object and the other object is really strong, so it knocks off the electrons in the air, causing them to be able to be conductive, to be able to conduct electricity. And therefore these electrons can jump through the air because it's conductive to the person and flow through the ground, and that is what we know as a spark, and that's what a spark is. So what I'd now like you to have a go at is these questions here to test your understanding on the topic. So pause the video now. Okay, let's go through the answers then. So we've got a shape here. Is the central charge in the diagram positive or negative, and how can you tell? Well, we know that it must be negative, and that is because the arrows are pointing in. Okay, so in a negative charge, arrows point in. If it was a positive charge, the arrows would point away, but we know it's a negative charge because the arrows point inwards. So are the charges shown below equal in magnitude? Explain why. Well, no, they're not equal, and we know that because B has more field lines, or the field lines in B are closer together, and therefore they are not as equal in magnitude, and you can see that here and here. And question 3, which charge A or B is larger and why? Well, we've just said it's B, and again because the field lines are closer together. What is the type of charge in diagram A and B? Well, again, we know that this charge is positive, and it's because the arrows point away from the charge. So the arrows point away, and therefore we know it's a positive charge. And finally, what would happen if charges A and B were placed close to one another? So both A and B are positive, and therefore when we know that a positive and a positive will repel, so we know that they must repel. Okay, when they enter each other's electric field lines, they will repel. They will experience that non-contact force, and that force will be a repulsion, and they will repel each other. So we've now then looked at electric field lines. There's plenty of practice on this on the website, and as ever, if there's anything you didn't understand, then please do get into contact with one of our tutors who will happily help.